Hello, Stats class. Here's lesson 6.3b, which is about binomial distributions continued, and a little bit about how they relate to normal distributions. Before we go into the new stuff, I want to show you some calculator shortcuts for what we learned in 6.3a. So this is something we didn't get to in the last set of notes. We saw in 6.3a, well, let's do an example out of the warm-up, actually. In the warm-up, we saw an example where we had to do the probability of getting 2 correct answers on that mini quiz out of 5. Anytime you see 2 out of 5 or number out of number, that's a clue that it's a binomial situation, which is another way of saying the probability that x equals 2 given that x is binomial. And we saw the formula for this that looked like this. And it was the number of ways of choosing 2 out of 5 times the probability of success to the number of successes, probability of failure, number of failures. And I made you explain each part of that, and hopefully we talked about it already while you were working on the warm-up, and I hope it made sense to you. Regardless, we got 0.264 for this. Now you could do that on every single problem, and actually I really like this formula, which is why I taught it to you. But I want to tell you there's also another way. I'm going to write it in symbols first. The probability that x equals k, our book calls it k, would be c n k times p to the k and q to the n minus k. And that is the official binomial probability formula. One of my favorite formulas. That's why I taught it to you without the shortcut first. The same thing can be accomplished with a calculator command called binomial PDF. PDF stands for probability distribution function. You don't have to know that, so don't write it down unless you love those things. But you need 3 numbers to tell the calculator. You need to tell it what n is, what p is, and what k is, so npk, and we could do that same exact thing with the binomial PDF function, and it would be faster. So like I could type this whole thing, or I could go into, it's the second vars menu, same menu where NormalCDF is, so PDF, CDF, all of those are in this menu. It's down towards the bottom, scroll down a ways, you'll see there's a lot of different distributions with PDFs and CDFs, and we want binomial PDF. And then we want to tell it the n, which in this case is 5. I should write this out. N is 5. P is the probability of success, which is 1/4. And K is how many successes, which in this case is 2. If you don't have the little menu thing on your calculator, because the older ones don't, then it looks like this when you type it with commas in between, and that's how I usually write it down. And you get the same thing. You get 0.264. Now, one of the reasons for teaching you this formula is on the AP test, this formula counts as showing work. This does not count as showing work unless you label these things with what they mean. So they're very picky about that. You cannot use calculator commands as showing work unless you label everything, and you could label this as N and P and K, and then they're happy. And I don't know why they're so picky about that. I guess my best guess is it's based on college professors not necessarily knowing this command. But I don't know. Just show work very thoroughly if you're going to use this. Label everything, and then you'll be fine. But this isn't the most useful thing on your calculator because you could do this, right? But there is another thing that's more useful, and that's if you want to do a less than or equal to, like that. And let's just think about what we would have to do. In fact, you did this in the warm-up at least once. Find the probability of getting 2 or less correct. So you could find the probability of 2 and find the probability of 1 with the same formula and find the probability of 0 with the same formula and then add the 3 together. And you had to do that at least once in the warm-up. But there's a faster way. And when you have, like, let's say you had more than 5, it could be like 50 things you have to add together, and that'd be terrible. There's a thing called binomial CDF that does this. C stands for cumulative, and that's the cumulative relative frequency that we learned way back. It's the less than or equal to. So if you're wanting less than or equal to, you could do that same thing with the NPK. And if you wanted the probability of less than or equal to 2, you would just do, instead of second vars, instead of PDF, you would do CDF, and you could still enter the 5 and the 1/4 and the 2, and this would be the first 3 entries in the table added together, or last 3, depending on which way your table went. So this one comes out to be 0.896. I don't think we even need to write that down, but that would be probability of 2 or fewer. Maybe I'll write it this way. 2 or fewer out of 5 would be 0.896. All right, so that's a shortcut that is going to be useful for some things that we'll be doing later on. You could also go the other way. If you want to do greater than or equal to, you have to do a little bit of fiddling with it. So if I wanted the probability of x is greater than or equal to 2, for instance, I would do 1 minus the probability of x is, let's think about this for a minute. Greater than or equal to 2 means 2 or 3 or 4 or 5. So opposite of that would be 1 or 0, less than or equal to 1. So you'd have to do binomial PDF with a 1 minus. N would still be 5, P would be 1/4, K would be 1. And I'm just going to do this to say, if you change this to a 1 instead of a 2, it does the complement of, if I do 1 minus, here's what I'm trying to say. If I do 1 minus, that would give me greater than or equal to 2. And that's kind of a mess, but those are the general calculator commands for exactly equal, or less than or equal to, and then here's the workaround for doing greater than or equal to. So I wanted to show you that before we go on to the new stuff. I'll come back to that at the very end because I want to compare and contrast 2 different methods. But before that, let's talk about shape, center, and spread. And we've done this a little bit in the warm-up also. The shape, you looked at the shape of the distribution that you were working with in the warm-up, and it turned out to be skewed right. And I actually even made you explain why it was skewed right. And so let me just draw it real quick. It came out looking something like this. And the boundaries are 0 right and 5 right. There's a pretty good chance of getting 0 right. There's a very low chance of getting 5 right because the probability was 1/4. And I asked you to explain why skewed right made sense. And whether you did before or not, I'll tell you, it's because you expect to get less than half of them right when the probability is only 1/4. So the reason it's skewed right is because that probability was less than 0.5. It made sense that less than, here's 0.5 or 2.5 problems right, impossible, but most of the time we were getting 0 or 1 or 2 right on this quiz because it was a small probability, that 1/4 probability that we had. If P comes out to be greater than 50%, you probably could guess that would cause most of the data to be over here, and then it would be skewed left. That's an LE. Sometimes I write left and it looks like a 6. Sorry about that. And then if P happened to be equal to 0.5, I could make you guess this if we were live in class, and somebody would probably guess that that means it's symmetric. I wouldn't go so far as to say it's normal because we don't know if it would be normal or not without more experimentation. It's symmetric and it might or might not be normal. It might be symmetric and something like this that's not close enough to normal for me, depending on how big n is, how many different possible outcomes there are. So all you can really say for sure is it's symmetric. We'll come back to that. Center. So again, in the warm-up, I had you do kind of a gut feeling for how many would you expect to get right on this quiz of 5 problems, and you're supposed to get 1/4 of them right. And you should have guessed somewhere around 1 or 2 because 5 times 1/4 is the common sense thing that you should do with this. If there were 8 questions, we'd expect to get 1/4 of them right or 2 questions right. This doesn't come out perfectly, but that's okay. It's 1.25. But we don't want to round it. We don't want to say we'd expect to get 1 right. We'd expect to get somewhere between 1 and 2 right. So that is the mean of all possible samples of size 5, all possible quiz takers' scores, if they're just guessing. The mean of all their correct guesses would be 1.25. And that's the expected value formula for binomial. It's actually one of the easiest formulas in our book because it is 5 is the number of trials or sample size. Actually, I shouldn't put it as a 5, I should put it as an n. And 1/4 is p, which is the probability of success. So we've got the number of trials, we've got probability of success, and it makes sense to multiply them together. You can also prove that this formula works by doing what we did in the warm-up, where you make the whole table and then you do the expected value formula with the table, and you can use that if you wanted to do some algebra and prove it, you could. It's a little bit complicated, but not too much for those of you who are really good at algebra. So anyway, that's the formula for the mean of a binomial distribution. You just take the number of trials times the probability of success, and it's a common sense thing, and I like it. It's an easy formula. Spread is not so easy and not so intuitive, so I'm just going to give you the spread formula and say it is this. I also have this one memorized because it's short, but you don't have to memorize it. You're going to write it on a weekly summary. Square root of NPQ. And because somebody always asks me what Q is, the book writes it this way. It is NP times 1 minus P. Remember, Q is always 1 minus P, or Q is the probability of failure. So that's the formula for the standard deviation. I did not make you do that in the warm-up because I didn't think you could figure it out just intuitively. It's not something you would guess, but I'll do the warm-up problem real quick. The warm-up standard deviation is square root of 5 times 1/4 times 3/4. Do all the multiplication before you square root and you get 0.968. So this is our average number correct. And this is our typical deviation from the average. How far above and below the mean you'd expect to be. And if you look at this graph, it makes sense. I believe on the warm-up, I put the mean on there for you at 1.25. That's the mean. And then you'd expect to be above or below that by about 1, a little less than 1, and that seems about right. And sometimes a lot more above, depending. Okay, so that's the shape, center, and spread information. Some of your homework will just ask you to calculate those like I just did with these examples, short examples. Sometimes they'll ask you to do something else with it, which is what the rest of these notes are about. So let's do one more thing, and that is, why would you need to be able to calculate these things? The main reason you need to be able to calculate them, I mean, I'm trying to go beyond the homework will ask you to, right? The homework will ask you to, but why? Why is this important? It's because if you have a big enough sample, then that shape is not just symmetric, but approximately normal. It smooths out the curve and makes it closer and closer to normal. And we're going to see that actually happening visually in chapter 7 when we play around with taking random samples from different things and seeing what happens with that. Right now, you're just going to believe me that it happens, and I'm not going to try and show you yet. But this skewed right, skewed left thing goes away if you have a big enough sample, and also the symmetric becomes not just jagged symmetric, but normal curve, because basically bigger samples make this just become perfect. And like I said, you'll see it in chapter 7, I promise. Right now, you're just going to believe me. What this is called is the normal approximation. And so part of what I'm telling you now is kind of old-fashioned because you don't need it so much anymore. We could just always do NormalCDF, but this was invented as a way of getting around that idea of taking this formula and adding a whole bunch of them together. Somebody thought, well, wouldn't it be nice if we could just approximate it? And this was how they did it. I'm showing it to you because we use it for a lot of things, even now that we could do it more accurately. So this big enough thing, I have to tell you how much is big enough, right? So big enough sample means that your sample size, this works, this normal approximation thing works if your n times p is greater than or equal to 10 and n times q is greater than or equal to 10. And again, we're going to see that in action in chapter 7. So right now I'm going to have you just trust me on it. People experimented with this until they found a guideline that looked normal enough to them. Think about NP for a minute. NP is our mean, the mean number of successes in n trials, or it's the expected number of successes. It's the number of successes that you expect to get in your n trials. NQ is the mean number of failures, or expected number of failures. So if your sample is big enough to have at least 10 successes and 10 failures, then it's big enough to assume that it's approximately normal. So let's do an example with type B blood, which is 35% of the population. And because I want this to be a big sample and not a little sample, I'm going to say, let's do a huge sample of, say, 1,000 people. Test their blood. And I want to know, I'm expecting to get 35% of them, so expecting 350 of them to have type B blood, but it wouldn't always be 350, right? Sometimes it'd be slightly more, sometimes it'd be slightly less. Let's go 360. Let's say, what's the probability of, in my sample of 1,000, that X is greater than or equal to 360? Or the probability that I get more than 360 people in this sample that happen to have type B blood. So the probability of 360 or more type Bs in my sample. There are two ways to calculate this. Method 1 is with Binomial-CDF. Method 2 is with the normal approximation. I'm actually going to do both because I want you to see that they come out very close to each other. They won't be exactly the same, but they'll be close. So I'm going to check to see if it's approximately normal. And what I do is I take my n is 1,000 times p, which is 0.35, and that's the 350 that I'm expecting to get, bigger than 10, good. And then I take 1,000 times my probability of failure, which is 100 minus 35%, which is 65%. I'm expecting to get 650 without type 2, or type B, I mean, and that's fine. That's also bigger than 10. We're checking that because that means that if we do a normal approximation, it should come out really close to the accurate calculation. So because it's approximately normal, this is okay, I can find a z-score. And then I could do a normal CDF. That's what I'm going to do. So 360 minus my mean. I just calculated my mean, whether you knew it or not. That's the 350, that n times p thing. Divided by, I should find the standard deviation because I haven't done that yet. So I need to do 1,000 times 0.35 times 0.65 and square root it. So I got 227.5 square rooted is 15 or so. I'm going to round it to 15.1, 15.08, close enough. Okay, so I'm going to put 15.1 down here. And my z-score is 10 over 15. 10 over the answer. I'm going to keep all those decimals to make it accurate. So z is 0.663. And then I want to find the probability of z being greater than or equal to 0.663, and that's a normal CDF problem, or use the table. This would go first since it's greater than, and 999. And so I guess what this does is it changes this type of problem that we're just now learning into a problem we've seen before. So maybe that's a good reason to learn how to do it. 999, and paste, and I got 0.254 is the probability of getting 360 people out of 1,000 or more with type B. This is the approximate answer. It's not perfect. it's going to be close. If I want to do exact, I could do greater than or equal to, I don't have a command for, but I could do 1 minus the probability that x is less than or equal to. If it's greater than 360, that's 360 or 361 or 362. To go less than, I'd need to go 359. Binomial is discrete, and so we have to think about that with binomial, so that's a little bit picky. But this is the accurate, more exact answer than what we just did. 1 minus binom CDF, and n is 1,000, and p is 0.35, and k is 359. And it should come out close. I guess I'm not quite positive because I changed my example this year, and if it doesn't come out close, I'll be embarrassed, but that's okay. 1,000 and 0.35 and, oops, 0.35 and 359. And it is close, 0.264. So it's only off by about 1%. That's not bad. So this is the approximate, which is an estimate of this, which is the exact. You could do it either way. There are reasons why later we're going to mostly do it this way. And that's what one of the things that's in your homework is they're going to ask you to do this normal approximation method when you can. If you can't do normal approximation because these don't come out big enough, then you have to do it this way. All right, so that is it for today. And then Wednesday, we will talk about one other special type of distribution called geometric coming up Wednesday.